Спасибо. Мое спасение. А то каждый раз, да, по новой все это.
Нет, это просто можно то, что его не доделали к 2022 году, ну или как-то.
И теперь не доделают.
Он open source.
Ну тем более. Ладно. Ну хорошо. So today I wanted to start a new topic and to make some calculations about Lie algebra later. So I want to speak about fixed point theorem and Jordan decomposition. So maybe I shall start with Jordan decomposition. Yeah, so let us start. This will be main tool in studying in introducing different types of algebraic groups. So this will be important for us, decomposition. Yeah, so first we shall start with recalling the following property. So what we're interested in, we have the group in GLV, so in the invertible matrices, so this will be algebraic group. And or we have the Lie algebra that, so notice that the tangent space in GLV, since it is an open subset of the vector space, is identified with so since it is open subset of the vector space, so this is identified with the vector space itself, which is isomorphic. So GLV is an open, so it's in endomorphisms or in n by n matrices. And this identifies this with the corresponding vector space. So since it lives as an open subset, so determinant is not equal to 0. Yeah? So we shall be interested in decomposing the elements. So there is a famous, so you start with an operator, and it is well known that it can be decomposed as follows. So I shall start with saying some, so I want to be more canonical in the setting, because it is well known that a matrix has a Jordan form, but it is more convenient to start with the objects that are defined intrinsically. Yeah? So that these are first eigenvectors, so which are the kernel of A minus lambda E. So this is a subset. This is a set of eigenvectors. A subspace of eigenvectors of value I, yeah, so with eigenvalue I. with eigenvalue lambda. Yes, so this, if you apply this directly, you get that it is just the set of vectors where AV is just lambda V. Yes, so this is eigenvectors. Or you may generalize this thing and consider the subspace which are kernels of the powers of this operator. Yeah? So this powers. So you have, and you see that these kernels are, of course, you have, they are contained in one in each other. Yes, so you the kernels with lower number are contained in the kernels with higher number. Yes, so this is increasing sequence of subspace. Of course, it stabilizes, and at least you can estimate that k is equal to m. Yes, so to dimension of the vector space. So you have this increasing sequence, and you notice that when you do the linear transformation, so just the conjugation, yeah, so it if you change a if you change it by the matrix, so if you change the coordinates in the matrix, then this kernels will be also changed. So the kernel of C inverse minus lambda E in the power k is just equal to C kernel of A minus lambda A. So this means that the kernels are conjugating consistently with the operator. And you see that, so you prove in...
C inverse kernel then C, no?
В смысле? Нет, ну я просто применил к этому оператору. Они, ну как бы... Не, в смысле, это не, вы правы, в смысле, без, на векторных пространствах мы, это же не операторы, да. Ну, просто вот так. So, ну, в смысле, что у нас действие на операторах вот такое, да, чтобы действие на векторном пространстве было стандартным. Ну, yes, of course, but what I mean is just that this linear change of the coordinates on V. So the change of the coordinates on the operator via this action is supposed to be consistent with the action on V via just the translation. So of course you may check whatever you like, but I mean if you no, this is more or less evident. And what we have, one proves, yeah, so one proves that vectors with distinct, so that belongs to distant kernels are linearly independent. Yes, so that your vector space, yeah, so if you put this to be V lambda as the kernel of A minus lambda E n for n goes to infinity, yeah, so for sufficiently large n, then your V becomes a direct sum of this V lambda. Yeah. So you notice that if you take your operator, so and take so what happens if you restrict your operator to this eigenspace? Yeah. So this so in this case the operator becomes so A minus lambda E becomes nilpotent. Yeah, of course. So just after you restrict it to V lambda. So this is evidently, and in the end of the day, you are writing down the matrix in the form that you are writing down it. So on the diagonal, you know that you have vectors lambda, and this up the diagonal, you have Jordan blocks where you have units in these blocks. Yeah. So what I need, what I need about this, so actually, if you like, you can think of this operators as follows, simply by thinking that you have, for the operator, you have so you can introduce the characteristic polynomial. And so, of course, if you substitute the operator in this characteristic polynomial, you have the corresponding vanishing. So if you, and your lambdas are just roots of this characteristic polynomial. And this, if you look at this polynomial, then you see that if you substitute matrix in this polynomial, you see precisely that it is a product of the corresponding. So n lambda will be the dimension of V lambda, and n lambda I. Yeah. So you see that, notice that in order to specify the kernel, that the kernel of this operator can be described as, so this is not a very complicated proposition, but you have to prove it, that if it is, so this should be taken, so the kernel of A minus lambda I and lambda can be identified with the image of the complementary, so of the product where the corresponding I is emitted. Yeah?
Lambda is number of block, not of eigenvalue.
Yeah, so of course, in the end of the day, you may think that it is. It doesn't matter here. I mean, of course, I mean for the statement, it doesn't matter, because when you are thinking about the other operators, so if you take, yeah, so let me state it. Yeah, so notice that if you restrict A minus lambda I E to Vj with different J, yeah? So here it will be invertible. So this is this will has no kernel, and so this means that, so notice that, of course, all V lambda J is invariant. So V lambda J is invariant with respect to A minus lambda J E. Yeah? So you can restrict the operator to this vector space. And on this operator has no kernel on V lambda J. So it is invertible. And whenever you apply any power. So you are proving even that this operator without power has no kernel on V lambda j, and if you apply it several times, then you are just so you do nothing. Yes, so you do not spoil your particular eigenspace. So you want to get as a kernel of A minus lambda i.e. you want to get precisely this vector space V lambda I, and on this vector space all these operators are invertible. On the other hand, they all commute and they annihilate the remaining V lambda I. Yes, so this operators annihilate. That kernel of this operator can be written as the image of this operator. Ну, где вот тут ишка стоит, вот, а здесь все кроме ишки. И вот, ну, ядро вот этого оператора совпадает с образом вот этих. Ну, почему? Можно посмотреть как бы непосредственно на вот эту сумму в лямбдаитах и увидеть, что когда вы применяете вот этот оператор, он аннулирует все, so this operator, so let it put it B, it annihilates all V lambda except this V lambda I. Yes, so this operator B annihilates all V lambda J except so V lambda J except V lambda I, and if you restrict it to this particular V lambda I, it has no kernel. So it has no kernel on V lambda I, since it is a product of operators that, so since it is just the product of B lambda 1, so the corresponding operators, B lambda k, yeah, so where B lambda I preserves V lambda I and has no kernel there, and has no kernel there. So this actually is a standard, just part of the proof of. I mean, at least as I have an impression on our faculty, it is a standard part of the proof of this theorem. However, here I want to say some small remark and about Jordan decomposition, and that's why I'm recalling all of this. Yeah. So what I want to say is the following. So if you have, so you can introduce semi-simple elements. So an element. So A S is called semi-simple. Semi-simple. If it is diagonal on some basis, is diagonal in some basis, or just to say in the same words but in different manner, it's all its eigenvectors form the basis. So there is a basis formed by eigenvectors. So so we shall need also nilpotent elements. So an is called nilpotent. If it is nilpotent as an element of the algebra, of associative algebra, so if it is just its power is equal to 0 for some n, and so here we shall need also unipotent elements, so U is called unipotent. If you can write down 1 minus u is nilpotent. So this means that all eigenvalues are 1. Yes, so it is convenient to say this. So this property can be written algebraically. So this gives you actually a polynomial on the coefficients of the operator. So it is convenient to. So it is important to have this kind of definition, but if you want to apply to the standard forms, so all eigenvalues are equal to 1. So equivalently. So what you want to do with the separators, if you have this, so if you are able to write down the matrix in Jordan form, so clearly you can decompose it as the sum of diagonal operator and nilpotent operator. Yeah? So just Jordan decomposition. Is just writing A as a sum of a semi-simple operator plus nilpotent operator. So semi-simple and nilpotent. Yeah, so this I won't prove, but yeah, so this means that, yeah, so since we are decomposing the elements, an element in the sum, then you see that it is just, yeah, so you are looking at this element as endomorphism of E, yeah, so you are decomposing it. And you may think of A as an element of some Lie algebra. Mm-hmm. Yeah, of course. I mean, if you are not over algebraically closed field, then you are passing to algebraically closed field. So to its algebraic closure in order to work with it. So I want, so this is what I have said is very well known. A little bit less known is the following. So you have this decomposition, and the question is, can you obtain the operators AS and AN from the operator A by some procedure? And the answer is the following, so that there exists a polynomial P. So P of t that belongs to the set of polynomials. So such that, so this is proposition. So such that P of 0 is equal to 0. So it has smallest coefficient to be 0. And just P of A, so if you apply this polynomial to your operator, then you get AS. Semi-simple operator. Yeah, so of course the same holds for, and the same holds for the nilpotent part. So you have this operator P of 0, Q of 0 is equal to 0, and Q of T is equal to A of n. But of course, remark, of course, when you already know P, Q is just is equal to, so Q of A is equal to A minus P of A. So as a polynomial, Q of T is just T minus the corresponding polynomial. So you see that it also has the lowest coefficient to be 0. So this is, yeah, so let me give a proof of this lemma. So what you have to do is the following. So what you have to just, so in order to, so you have to give some conditions on the polynomial, and notice, so notice that for different eigenvalues, A minus lambda I E are pairwise coprime. Yeah, so Ni are pairwise coprime. So you can actually take the for Ni, you can take Ni to be put put the maximal. So there is a maximal degree when this just there will be a minimal degree when your thing will stabilize. Yes, so that the kernels.
Matrices are coprime.
Yeah, so polynomials are coprime. So put for Ni. So let us put it Mi, for example. I mean, for Mi, put the value, the minimal value, where A minus lambda IE Mi is equal to A minus lambda IE Mi plus 1. You see that this vector spaces, this is an increasing sequence of the vector spaces, but they have bounded dimension, so in the end they will stabilize. So these are coprime, so you can use the Chinese remainder theorem. To have the following application. So just put the polynomial P of T such that it will be equal to, so notice that how to characterize this semi-simple operator. Simply if you have, so simply if you restrict, notice what you want. So you have this kind of block, yeah, and it is, I mean, it is consists of some Jordan blocks. So this is a space V lambda 1, and if you restrict the AS on V lambda 1, this is just diagonal part with the same eigenvalue. So this is just lambda 1 times identity operator. Yeah. So if you restrict the semi-simple part to the corresponding eigen space, then you get that it is just lambda 1 times identity. And you search P of t to be the following polynomial. So it is just lambda I modulo this kind of polynomial.
P and Q are not universal polynomial for computing AS and AS.
Yes, so there is no way to, here at least, to write down AS as universally that doesn't depend on operator. But if you have already a bunch of eigenvalues, then you have this polynomial. Okay? I mean, this polynomial depends only on the set of eigenvalues. Yeah? Okay?
You mean that you can construct...
I mean that whatever the nilpotent part is, it doesn't matter. You just have this polynomial. If you have the problem, just if you write down a test work on geometry and gradients, of course, if you have one operator and the other, and they have different eigenvalues, you do not have to, and he asks to find the polynomial that gives you semi-simple part, then you are just taking the same polynomial for this.
How is it so that PT is a polynomial?
Yes, I mean,
Minus lambda E
is a polynomial.
Polynomial with matrix coefficients.
Нет, извините, ну да, тут, sorry, это оттуда пришла опечатка. Просто подбираем полином, ну как бы, чтобы он был равен, ну как бы вы можете подобрать любые остатки, но вы выбираете просто лямбда и t. Так? Вот по модулю вот этих дел. Но они все взаимно простые, вы можете сделать. Ну еще, so you have additional condition like this, yes, so that you are just having P of t is equal to 0 modulo t. Yeah, so what you get when you apply P of A, yeah, so just
Can be lower upper bound degree of.
ну, в китайской теореме об остатках вы умеете находить максимальную степень? Ну, в принципе, да, потому что вы по очереди это делаете. Ну, как бы.
Попадает в остаток модуля произведения.
Да, да. Поэтому, ну, как бы, if you have, now we have to check this, what I have said. So what happens that if you apply A? Yeah, so if you apply A to this polynomial, what happens when you restrict it to the space V lambda I? Yeah? So on V lambda I, so if V belongs to V lambda I, then you have that A minus lambda I E in the power mi applied to V is equal to 0. Yeah? So this means that if this thing really tells you that your P of t is written as, so this means that P of t is written as the polynomial lambda I plus z, which is some polynomial applied to t minus lambda I mi. Yeah, so you are applying this polynomial. This is polynomial without highest coefficient. And of course, this annihilates v. Yeah, so if you apply this to v, so P of A applied to your given v, is just lambda IV plus. So maybe it is better to write it down as, sorry, here, of course, I have written it badly. Yeah, so it is T minus lambda I mi times some polynomial z of t. And if you apply it to v, then of course this is z of a minus lambda I mi applied to v, so this is 0. Yeah? Да.
There is a faster way to say this because like if polynomial operations falls in some basis, then in Jordan basis too. And
Нет, ну вот этим вы можете теорему Жордана доказать, кстати. Поэтому как бы, поэтому я, ну просто вот это вот как бы мне нужна вот только вот эта часть, но реально она воспроизводит теорему Жордана, ну по доказательству. Поэтому вы уж извините, я просто не знаю, как, ну кто как рассказывает конкретно, поэтому. А?
представил, D2 на 2 диагональные матрицы, какие будут уравнения вот с модулями. Вот там просто какая-нибудь матрица типа 1, 0, 0, 2.
Ну ладно, ну короче, ну вот здесь вы давайте. Вот, согласны? So this is just lambda I of e, and this tells you that if you restrict, since you know that something is a direct sum, then you know that the restriction of p of a to each direct summand is just lambda times identity. So this is precisely the condition of being diagonalizable. And so the remaining part, yeah, so if remaining part will be nilpotent. So of course, if you write down p of t and write down something like this, yeah, so a minus p of a. So t minus p of t is just 0 modulo t minus lambda I mi. So this tells you that just restriction of a minus lambda I e on it really tells you that when you take your operator and substitute it, so the restriction of, so if you put it to be q of t, restriction of q of a to the corresponding eigenspace is nilpotent. Yeah? So just by definition. So this is precisely how it is nilpotent. Yeah? So so you have decomposed the operator in the sum. And why this is important for us? Yeah, so why this? So this is because of the following proposition. So assume that you have you have two vector spaces, so that u and w such that u is contained in w. So these are linear subspaces. Linear subspaces. And suppose that A of W sits inside U. Yeah? So then yeah, so A of W sits in U. So where A is an operator from V into V. So a linear operator. Hmm?
Why t minus pt just in mod t minus lambda I
So I just wanted to subtract it, the operator.
After the module, you get t minus lambda I not 0 there, right?
But if you restrict A to the corresponding
if you have that thing when restrict to v to the power of lambda, you just get directly 0, not Unipotent.
this one.
This one, yeah, yes.
No. This is a zero polynomial, but this is zero modulo this value.
Yeah, but I don't see this thing.
Huh?
I think you get t minus lambda I not 0 there.
Yeah, so here it's not, yeah. So here it's not zero, yeah. Just, yeah. Just take this operator. Yeah, so this is so this is not so evident. You have to so here, of course, you have to prove something. Yeah, so here you have to prove that the operator, when you restrict it to the corresponding. So here you have to prove that if you have so if you take the corresponding eigenvalue, you restrict your operator, then this it has only eigenvalues corresponding to lambda I, and it can be written somehow at least at the upper triangular form, so that you have to pick up the basis consistently, so that I mean, there is there is some part of the theorem of Jordan. So that's why I'm saying that I'm not proving Jordan decomposition theorem, because here you have to, in order to prove that it is not just that. So what you have to establish that if you have the restriction of the operator on its eigen corresponding eigen space, then it has a diagonal form with corresponding lambda I on the diagonal. So if you subtract lambda I, then you get an nilpotent operator. So this I do not prove. So we are constructing of Jordan basis. Yeah, so if you like, we can discuss it just after the break, so after the class. So then you are assuming this kind of thing. So I want to notice the following, so that if you, if you have the property that A of U sits in W, in this direction. Yeah, so that then we claim that the semi-simple part of U sits in W, and the nilpotent part of U also sits in W. So Yeah, so maybe
Is it true that we can just replace W by
the same.
the same?
Yeah, so maybe let us put the same. I mean, not to just. Yeah, so let us put the same for simplicity.
It will be not equivalent.
Yeah, it will be not equivalent, but
Why not equivalent?
Why equivalent?
ну, как бы, это ж как бы требование на оператор.
It's in W.
Нет, он же необратимый.
If image U is in W, you don't mean
Yeah,
image
so.
of whole W is in W.
So this, let us put for simplicity this one, and we shall prove it. So why this is true? So note that. So the proof is via our construction of the polynomials. So this is this goes as follows. So you have the polynomial p of so as applied to u. So as is just a polynomial in A. Yeah, so it is the powers an, etc.
But this works only
Plus.
for U, but not for U and W.
Не, ну сейчас как бы давайте. Нет, если вы их в правильном порядке сделаете, то все сработает. Вот если вы скажете, что вот тут U, а тут W, да, U меньше W, то требование должно быть, что как только вы A применяете, то W попадет в меньшее пространство. Вот.
Так меньше, все, иначе просто все очень странно. Так?
Ну, как бы я же вам не просто так, чтобы наврать, так сказать, или просто так поговорить с вами. Я все-таки там теоремы рассказываю. Вот.
То есть W, да, лежит в.
Да, ну, как бы тут.
В смысле, там не U, а W.
Где?
Вот A W, да?
Да, тут W.
Нет, выше.
Да. Угу. Что вы как бы.
Ну, вначале так и было.
Ну да.
Совсем вначале.
Ну, как бы я решил для вас упростить, а потом все-таки, когда написал, я еще раз решил усложнить. Ну, как бы в чем дело? So what is the reason for this? You are writing AS as the linear combinations of powers of A, and of course, so notice that so why have we have done this additional property? Notice that, yeah, so here you have to notice that if you are using this additional property, that is actually is consistent of the corresponding, I mean, this is not spoiled if, even if you have zero eigenvalue. So this kind of condition really tells you that you have to add the additional condition that is more strong. Yes, so possibly if lambda I is equal to 0, then you add that P of t is equal to 0 modulo some higher power. So this this doesn't spoil anything. Yeah, so just so so this condition is not contradicting one. So and if you write down now the polynomial AS as this linear combination, of course you just use that A of W will be inside the U, which will be actually again U is a subset of W, and you can apply again and again. Yeah, so apply inclusion again.
Sorry, I don't understand one moment.
Да.
If AS and AM are polynomials of A, then they must commute.
Да.
But AS is diagonal.
Ну,
And AM is also diagonal.
нет, ну просто смотрите, когда вы ограничиваете на не так. So if you restrict, so there is one operator that commutes with everything. Yeah, so if it is diagonal with the same eigenvalues, it is lambda times E. And if you restrict operator A to V lambda, then it's if the semi-simple part AS restricting to V lambda is just lambda I times identity. Yeah? And this operator commute with any operator on V lambda I. So you see that just they really, this, yeah, so what you said is, doesn't mean. So you just apply this inclusion and do by induction that AS W sits in W, and the linear combination AI where I is strictly bigger than 0, then also applied to W sits in W. So you get that this polynomial is, notice that, so what is most important here, there is no constant coefficient. So that's why I was applying this condition. So P of A of W sits in W, and the A S of W sits in W. So this is a starting point of considering Jordan decomposition and actually trying to algebraize it. I mean, there are two options when you are speaking about Jordan decomposition, you can speak about it in the category of Lie groups and Lie algebras, or you can speak about it in the category of algebraic groups. And so more or less what we have said so far are the same for both of these theories. But then I want to, I mean, it doesn't matter, this is pure algebra now that is going on. But then at some point, these theories become not parallel. Yeah? So they go into a little bit different direction. So for algebraic groups, we have stronger properties. Yeah? So that also, let me mention the multiplicative Jordan decomposition. So you see, so we have decomposed A into AS plus AN. And notice that if A is invertible, so suppose A belongs to GLV, then you can immediately say that this implies that AS is invertible. Yeah, so otherwise you have eigenvalue 0, and for the 0 eigenvalue, so otherwise the kernel is non-trivial, then via lambda 0, where lambda 0 is equal to 0 is non-trivial. And this implies that when you restrict A to this V lambda 0, then since AS restricts trivially, it is just AN, so this is nilpotent operator. Nilpotent. So you see that AS is not invertible there. So, since AS is invertible, you can write as follows, simply AS 1 plus AS inverse AN. And so notice that this is still the same element. And what can be said about this one? So clearly, AS, so we know that AS and AN commute. So AS and AN commute. Then you notice that this implies that this operator is also nilpotent. Yes, so that AS inverse AN is also nilpotent. And this implies that this operator is unipotent. Is unipotent. Okay. So no. Yeah, so also there is funny remark related with these types of operators. Yeah, so remark on Jordan decomposition. So first I want to make a remark in characteristic 0. So for characteristic of k is equal to 0. And this is as follows. So you may connect so if you have unipotent operator, so if you have nilpotent operator, n is nilpotent, so A is nilpotent. So this notice that you consider it as a matrix. So just as a matrix. So this sits inside matrices and by matrices. And so you can pick up, A to some power n is equal to 0, and you can consider exponent of A, which is simply the series for exponent. But it terminates, yeah, because of the nilpotence of operator. So this is polynomial map. Yeah, so this is polynomial map.
Why the opposite operator is invertible?
What?
Do you write that A is nilpotent and A is invertible?
Well, sorry, no. Yes. So if you can consider this exponent, not because the characteristics is 0, yeah? So you can map it to the set, so you can take the exponent and vice. So what you get unipotent operator. So this is unipotent operator. This can be seen as follows. Indeed, this second part is just A plus some polynomial R of A. And they, of course, commute. So this power A is nilpotent. So A in the R of A in the power n is also 0. Yeah? So also you have inverse map. So you have given a unipotent element. Then you have logarithm map. And this gives you that u divided by 1 plus u squared divided by 2, etc. So u to the power k divided by k. And yeah, so sorry, 1 minus u. Yeah. And yeah, so что-то не то. Да, yeah, so sorry. Yeah, so you are writing down the yeah, so you want to apply a logarithm to unipotent element. And this is just right. So you want to add 1 and like this, 1 and subtract 1 and write down like this, yeah? And if you write down the series for logarithm this way, then you are getting what I have written. And notice that why I have done this, yes, so that since u is unipotent, 1 minus u is nilpotent. So this means that this is nilpotent operator. Notice that if you are speaking about the subset in the matrix algebra, then of course due to Jordan decomposition, you know that the nilpotence degree is bounded. Yeah, so.
In the whole position in the remark about the image of nipotent operators under exponentiation lies inside the unipotent ones.
Yes, and this lies in the unipotent ones, yeah? And these are nilpotent operators because 1 minus u is nilpotent, and so you can even put it, I mean the sum of commuting nilpotent operators is of course nilpotent, but here you can even write it down like this. I mean here it's even more simple. Yeah? So
So it was about the sum of the nilpotent is nilpotent as well.
Sum of commuting nilpotent operators is nilpotent.
Is this maps invertible, invert to each
Yes, yeah, and this is not coincidence. Since the series are inverse to each other, these maps are inverse to each other. Yeah? So that's so this. So this maps are inverse to each other. So are inverse to each other. And also, yeah, so also we know that if you want to, so this exponent, yeah, so n times a, yeah, so it's just exponent of a in the power n, yeah. So suppose also, yeah, so there is also important proposition. So suppose we take the subset of G is a finite dimensional subset. So finite dimensional subset of invertible matrices or of nilpotent matrices. Subspace. I wanted to say subspace. Subspace of nilpotent matrices. Then what we know, since your matrix is, so these are matrices act on the same space, you can bound the nilpotence degree. Yes, so then for any A inside G, A to the power n is bounded, so is equal to 0. Yeah, so this is by Jordan decomposition. Чего? Ж готическая. Да. Ну, как бы про себя я имею в виду сейчас алгебру Ли. Но что я хочу сказать, что you can take exponent of G. Yeah, so this is a subset of unipotent elements. So subset of unipotent elements. So this is not proposition, this is more or less remark. And this is... Да. Yes, yeah. Yeah.
I'm not sure. How do you prove that the addition of two unipotent matrices is
I mean, suppose you take a G that consists of nilpotent elements. Yeah, so I meant that consists of some nilpotent. I mean, this is the space where all matrices are nilpotent. I mean, this is a property of the space. It's not arbitrary. Yeah? So this, I mean, it's evident that such spaces exist. For example, one-dimensional space. But of course, or just if you want to have example of such spaces, so this will be more or less all examples that we will get, and so this is, but it's not clear here. So at this moment, so you can take upper triangular matrices. So if you take any subspace here, it will behave, it will have the corresponding property. So if you put 0 on the diagonal, so all matrices of this form will be nilpotent, and it will be sufficient to raise it to nth power to get 0. Yeah? But this is example. This is not theorem so far. So just here I do not say anything about multiplicativity. So yeah, so the only thing, so it is not clear which conditions here we should impose that, so that the exponent of G will be a group. But actually, so there is so the theorem that if G is closed or maybe a proposition. So proposition that if G is closed under bracket, is closed under bracket, so meaning that you simply have to take the commutant of the matrices then exponent is a group.
Just a group.
Hmm?
It's just a group or algebraic subgroup.
Here it will be algebraic group because this will be, so this remark really tells you that this thing is algebraic map. Yeah, because it is just written in a bounded series. Yeah, so what we have so far, so if you use, so since we can bound the degree by the fixed number, you see that this map is polynomial map in coefficients of the matrix A. Yeah, so in coefficients of matrix A. So it will be also, if you have a set of matrices, it also will map so this means that you map regularly so you will have the following situation. So you will map G by exponent regularly to the set of matrices. Yes, so actually to the set of invertible matrices. And exponent will be a regular map, so meaning that it is polynomial map. And using this proposition, you get that if it is a group and it will be algebraic. So since it is a regular map, so image will be exponent of G is constructible subset. So constructible subset. So if you add the condition that it is a group, then it will be a closed subgroup. So closed algebraic subgroup. In GLE. Okay? So this tells you that taking, so this proposition is not so trivial, but you see that somehow there is this is how the exponent works. It gives you the corresponding bijection between the elements of Lie algebra and the elements of the group. And notice that here we can derive an important property that since you have bijection, so on the set of nilpotent elements, you have precisely the bijection. This means that, and taking into account this easy property, yeah? So, this means that remark, if U is unipotent, so suppose that characteristics again is 0. So if U is unipotent and U is not equal to identity, then it has infinite order. So as an element, then u in some power n is not equal to identity for any n. Okay. And the reason is that if u is unipotent, then you can pass by logarithm to 1 minus of 1, just logarithm of u is nilpotent. And you may write u again as just u as exponent of the logarithm. And so this just logarithm and exponent, they're bijective map inverse to each other. And you may write here, you may write so introduce n. So in order to write down u to the power n as exponent of n logarithm u. Yeah? But notice that exponent is bijective, and this is never 0 because it is an element of. So this is not identity, since exponent is bijective. And logarithm u, n logarithm u is not equal to 0 for any n. Okay. Yeah, so maybe it is a good point to make a break. So, yeah, so let us do the break. And after the break, I shall say something about characteristics, P. So. А?
Запись все равно будет.
Ну да. Нет, так я же микрофон выключил. Да ни о чем мы и не разговаривали. Вот. Yeah, so, okay. Yeah, so, and what about characteristic P? Yeah, so it shows that actually if you have the algebra formed by nilpotent matrices, the Lie algebra, then the exponent is a group that consists of unipotent matrices. But over in characteristic P, you cannot take, of course, this kind of map because for the simple reasons you cannot divide by prime numbers, by prime number which is characteristic. And in the series, all numbers are present, so what happens in characteristic P. So characteristic P case. So the claim is the following. So you have any unipotent operator. So U is unipotent. Then,
Is it true that previous lecture went such long way to prove some facts about matrices because now the matrices would be over the field with finite characteristics?
No, this was. I mean, we have recalled everything of for the following reason. Just how the Jordan decomposition behaves when you're passing to the group, to the subgroup. Just a second, I shall be talking about this. So let us, see what happens in characteristic P case. So suppose U is unipotent, so it is 1 plus nilpotent matrices, nilpotent matrix. And then you just raise it to 1 plus P. Yeah? So in characteristic P, as you know, this is 1 plus E P to the power n. And if n is smaller than P to the power n, then this is, of course, 1. So you see that all elements are of finite order, and this order is precisely the power of P. So all elements are of finite order of all unipotent elements. Finite order, which is a power of P. So So and if you are working, for example, over the finite field, so that if you have the elements which are defined over finite fields, then of course they form, they generate the finite group, which is not surprising. And just because of if your elements, so if you consider the elements that are just sitting in the matrices where coefficients are in some finite field. So this is just finite collection of matrices, and the group is finite. And for the finite groups, you can work as you can. So with the finite groups, you work via Silo theorems. So for example, this somehow play. You see that unipotent subgroups play is a P group actually. Yeah?
This violates my generation. Даже над алгебраически замкнутым полем ведь тоже будет вот ваш аргумент работать про то, что...
Ну, у вас может быть про... нет, этот аргумент будет. Я просто хотел сказать, что работать вы можете с матрицами. Ну, я хотел сказать, что работать вы с ними можете как с конечными подгруппами.
Вопрос, работает ли там Жгун-В.С форма?
Ну да, работает.
Тогда это как-то очень странно, ну вот, потому что у корневого вектора в принципе нет.
Ничего нет. Ну, как бы. Ну. Okay. So next part is the following. So now we can pass to Jordan decomposition in algebraic groups. Yeah, so Jordan decomposition. Какое? Про вот это не будем пока. Jordan decomposition of algebraic groups. Нет, в том-то и дело, что просто проблема в том, что ну вот это предложение, если бы вы, ну у вас все элементы коммутировали, оно было бы очевидным, потому что вы вот сказали, да, что so this proposition would be evident if A and B commute. Yes, so if A and B is equal to 0, then of course exponent of A plus B is equal to exponent of A times exponent of B. And in more general case, this is a much more complicated formula, which is called Campbell-Hausdorff formula, that tells you how to write down the exponent of the product. So actually, you are writing down the exponent of the product, the logarithm of exponent of the product, in terms of polynomials. Yeah, so if you put here two parameters, so you are writing down it as the polynomials in the brackets of A and B. Yeah, so you have different polynomials where you can compose A and B with the brackets, like here, like this, for example. And the answer is that the Campbell-Hausdorff formula tells you that this logarithm can be written as the infinite series in this commutants. Yeah, so it is quite long thing. So yeah, so what about Jordan decomposition? So now the idea is that we have to introduce some, we have to define what does it mean Jordan decomposition. So we want to define the type of the element. Yeah, so suppose you have an element now in the algebraic group. Yeah, so you want to understand when it is semi-simple and when it is unipotent. So then you have the action rho of G on the set of functions. And if you are interested, yeah, so here you notice that for any vector here, so for any function, so there exists a finite dimensional vector space. Such that just F is so finite dimensional vector space such that rho G preserves so the action which so rho of G, which is just rho of G of F, is just F of G inverse of X. Yeah. So this preserves this vector subspace. So you can speak about so the operator just is the finite. I mean the operator rho of G can be restricted to this finite dimensional vector space, and the claim is that rho of G is just so rho of G is called nilpotent. Is called nilpotent. Oh, unipotent. Ну, да, V содержит, да. Угу. Ну, как бы, что если вы интересуетесь действием на одном элементе, можно его, да, поместить в векторное пространство и работать только там. Yeah, so rho is called unipotent if this restriction of rho G to V is unipotent for any V. And which is invariant under rho of G, and semi-simple. If Да, ну то есть смотрите, как бы в чем проблема, что вы правы. Но вот если бы KG, so if K of G will be a direct sum of the representations, this would be evident. You can speak about the structure of rho of G just by saying that the restriction to each summand is should be nilpotent, and the restriction to each summand should be semi-simple. So here it is not clear, and it's not true actually, that K of G is a direct sum of invariant subspaces. So it's not clear that you can speak about being unipotent or semi-simple if you do not fix some vector spaces. But here you are taking all possible in G invariant vector subspaces, and you want that restriction of rho to this invariant vector spaces will be unipotent or semi-simple respectively. Yeah?
So when you write for any V, you mean for
any invariant V. Yeah, so
finite dimension.
yeah, so for any rho V in K of G such that dimension of V is finite and the rho of GV maps NV. Otherwise, you cannot speak about anything like this, like unipotent or semi-simple. And here, of course, there is not clear moment why this the type of the element really. So why this type of the element preserved. And now we can formulate the theorem on Jordan decomposition, which will make the life a little bit more understandable. So just proposition. There exists a unique Jordan decomposition Yeah, so for any for any G inside G algebraic group, there exists a unique Jordan decomposition G equal to GS GU. So such that if you have a homomorphism, so the images of this so phi, the Jordan decomposition for the image is just an image of the Jordan decomposition. Yeah, so phi of GS and phi of GU. So this is semi-simple. For H, yes, so for H. And this is unipotent.
Decomposition such that if we go inside that another group, then simple goes to
Yeah. То есть, ну, как бы в частности, если, so in particular, this means that so such that they commute, GS GU is equal to GU GS. Yeah, so this is the claim, just the what we obtained. Yeah.
Слово unique, оно к чему относится?
Ну, вот к разбиению, ну, вот как бы вот это вот, когда вы G зафиксируете, то GS и GU от... So if you fix G...
Оно до Sagittarius идет.
Yeah. So there is unique Jordan decomposition such that this holds.
And this holds.
Да, вот дальше.
So this holds. So this is the first.
So second is automatic hold.
Second is so it's a claim. So remark about what we have written for A. So notice that if you write A as a sum of semi-simple and nilpotent part, so notice that AS is unique since V lambda is unique. So
And what is unipotent in case of arbitrary algebraic group?
Нет, ну вот так.
Это уже.
Не, ну так специально же. Да. Ага.
So G is semi-simple if rho G is semi-simple.
М?
So you define G is semi-simple when rho G is semi-simple.
Там, где
You just define the semi-simple.
Yeah, I defined this semi-simple and unipotent elements for arbitrary element G. Yeah. So here. This AS is unique because when you restrict to V lambda, so V lambda is defined uniquely. By A, and AS is defined via the property that AS is just lambda, the restriction of AS on V lambda is just lambda, and this is characterizing property, yes, so that because it should be semi-simple, when you restrict to the corresponding eigenvalue, this should be semi-simple with prescribed eigenvalue. So there is only option that it is equal to lambda. Yes, so there are no other option for the operator to be like this, and a posteriori it commutes. Yes, so yes, and then so it defines AS uniquely.
Standard Jordan decomposition is unique to like additive version.
Yeah, additive version is unique, yeah. Because, не, ну просто потому что вот, ну как бы вот эти v лямбда, они единственные, ну как бы v лямбда, они внутренним образом определены. Если вы действуете оператора автоморфизмом, то v лямбда переходит... Да. Поэтому, но полупростая часть на v лямбда, она должна, ну как бы вы знаете, что это, она должна диагонализироваться, а собственных значений других на v лямбда больше нету. Поэтому там она диагональный оператор, ну и все, как бы такой оператор один при ограничении на v лямбда. Yeah, so by the way, there was the part where we have defined Q like this. Yeah, so just t minus p of t. I have just forgotten to say. Thanks for Chen for recalling this, that when you restrict Q of A to V lambda, this is just t minus lambda I. But modular, if you, A minus lambda I, but, sorry, this is, yeah, so, yeah, so if you restrict it, this will be A minus lambda I, but everything is taken to be a, modular A minus lambda. Yes, sorry. So this is for t, yeah. And if you recall that p of t is just lambda modular t of minus I, then you get this thing. And you see that this when you raise this element to mi, this will be 0. Yeah, so if you raise q of t v lambda in mi, it's just t minus lambda I mi is 0 modular this thing. Yeah. So this is the remark that I scrapped. So yeah, so this this decomposition is clearly unique from this kind of thing, and the multiplicative decomposition is also unique. Yeah, so this implies uniqueness of multiplicative decomposition. Which is A is equal to AS times AU. Yeah. So actually, yeah. So yeah. So the thing is that if you, of course, yeah. So the problem, of course, you may think that you are writing down. So it's not so clear that if you actually, without this observation, that if you, yeah, so as for additive decomposition, yeah, so this is more or less clear that it is unique without this assumption. Yeah, so if you write down this AS plus AN. No, it's it's not. So the problem is that if you write down the equality like this, so without additional assumption, so it's not clear that even if you put semi-simple part to one side and the semi-simple part and nilpotent part to the other side, so the problem that it's not clear that difference is also nilpotent and difference of semi-simple elements are semi-simple. So of course, if you compare two elements, semi-simple element is nilpotent, is unipotent, is nilpotent if and only if it is 0, and semi-simple is unipotent if and only if it is just all ones, just because for the conditions on the eigenvalues. And here, I mean, it's not clear that this is nilpotent because in order to prove that the sum of the difference of two nilpotent elements is again nilpotent, so you should assume something on commutation, so at least you can prove it when they commute, but I do not claim that we have this the case so this is the case in our situation. So so now the idea is to the idea is that if you have so when you know about this existence, so so note that if so this theorem is non-trivial because so also there is part 3 of the theorem, so just part 3, that if H if H is a subgroup, it's a corollary actually. So if H is a subgroup, then you can decompose H in the semi-simple part and this part. So what I mean is that if you take the element H here, so you can decompose this element H looking at the element G to the semi-simple part and unipotent part. And so, for example, in G you have a Jordan decomposition. Then you can decompose H into the semi-simple part and unipotent part. But nobody guarantees you that both semi-simple part of H just as an element of G so they will belong to the subgroup H. So nobody guarantees. A priori. So without this theorem. So not using proposition. That HS belongs to H and the HU belongs to H.
Can be that HS belongs to H, but we can make decomposition inside group H.
But and if you take in the same time, if you take the decomposition inside group H, so if we take So notice that still, so HS, so as an element, you can look at them as an element of G. So it's not clear that they are semi-simple in that setting. Yeah, so it's
It's one position.
yeah, so it's not clear that they are semi-simple. I would say as the elements acting on K of G. Yeah, so as elements acting on K of G.
Is it true that semi-simple is equivalent to like semi-simple in every finite dimension representation?
Yes.
Then it's obvious because every representation.
Then it's obvious, but you have to prove this, yeah. So somehow.
Could you explain it?
Yeah. So what I mean here that so you can take H as the element of H, yeah. So saying that you have decomposed it into the product of two elements, I understand this, that if you take rho of HS acting on K of H, it is semi-simple there. But also you have action of rho of HS on the bigger group, or on the bigger algebra, which is K of G.
Yeah.
And if this is semi-simple, a priori it's not clear that this is semi-simple.
Do we use semi-simple and unipotent interchangeably?
No, I mean, you can speak about either semi-simple or unipotent, but
Simple then.
hmm?
What is semi-simple?
Semi-simple is diagonal, unipotent is да. Да. То есть полупростой — это просто диагональная часть Жорданового разложения, а нильпотентная — это наддиагональная часть. Да. И поскольку там вся клетка берется со своим собственным значением одинаковым целиком, поэтому они и коммутируют. Да? Потому что для клетки диагональная часть, она как раз, ну, в смысле, что она как раз скалярная, то есть лямбда тождественный оператор. Yeah, so,
Semi-simple element in H is semi-simple element in G.
yes,
Unipotent in H is unipotent in G.
and I mean that a priori by our definitions it's not trivial. I mean, because we're checking semi-simplicity on the algebra of functions. Yeah? It's also not clear that this is well-defined notion actually, because you have to check it on all the elements. So on all finite dimensional vector spaces, it's not clear that such elements exist. So there are some slight problems, but I wanted to formulate this proposition in order to emphasize how we shall be proving this. So
Первую часть мы доказали уже, да?
нет, мы ничего не доказали. Вот, как бы, ну, кроме единственности. Ну, как бы.
Единственное, что если не равны, то мы их перенесем, да?
Нет, а это тоже нельзя так доказывать. Если мы их перенесем, то вы перенесете, вот это я тоже пытался рассказать, что это тоже не так очевидно. Вы перенесете, с одной стороны будут произведения полупростых элементов, но, возможно, в разном базисе. И у вас там как бы полупростой элемент, это значит диагонализируемый в одном базисе, а другой диагонализировался в другом. И вы не знаете, вы там взяли, например, какие-нибудь вот один вот такой элемент полупростой, а другой вот такой элемент. И вот кто знает, да, их произведение диагонализируется или нет. А справа у вас стоят два унипотентных элемента, Ну и там тоже непонятно, да, ну, например, если бы вы в сумме делали, ну, как бы сумму переносили, да, ну, для суммы, то если вы его перенесли, то там все равно вы его переносите, и там сумма разность двух нильпотентных элементов. Если они не коммутируют, вы тоже не можете сказать, что их степень нильпотентна. Ну а
что мы утверждаем? Мы не это утверждаем.
Нет, ну вот если вы теперь знаете, что G это произведение GS на GU, где GS это полиномы от G, а GU это полиномы от G, то тогда вы знаете, что они коммутируют.
В смысле полином? Сейчас.
Ну, в смысле, что полином, просто полином от G, ну, в смысле, как матрицу вы G
Это
рассматриваете.
же какие-то элементы группы.
Нет, если вы G рассматриваете как матрицу,
Представление смотрим. Вот.
то вы можете рассматривать GS как полином вот, в матрицах полином.
Сейчас, если мы знаем, что такое разложение есть, то мы ограничим на какое-то конечномерное V, вот наше оружие, да?
Да,
Смотрим матрицу какой-нибудь.
да, да.
И дальше мы говорим, что там оно единственно, да?
Там оно единственно, да.
То есть мы доказали единственность по модулю того, что существование,
Ну,
да?
если
Да,
элементы
да, да.
одинаково действуют на K уже, то они равны.
Да, да. Но они просто... Yeah, so the uniqueness is proved, but we need to check that it is, that it exists, yeah, because it's not clear that such such decomposition exists. Yeah.
When we talked about uniqueness, we need a factor like if two elements act same on K of G, then they are same. Can you recall?
But they act the same way on all elements,
Yes. So
which are embedded in the finite dimensional space.
So they act
So they act the same way on any...
on whole K of G.
Yes, because they...
So what?
Ну, в смысле, если у вас поэлементно два оператора одинаково действуют на множестве.
It was embedding of this action is embedding.
No, I mean that... нет, ну...
G to rho G is embedding. It is like...
Не, ну, вы про что? Что если два оператора действуют одинаково на все элементы K, G, они равны? Ну.
If rho G1 is equal to rho G2, why G1 is equal to G2?
Это вы спрашиваете. Я понял. This is because, so there was a question that if you, again, we discussed it, but that was a question about this is because the action of so you can check what is so suppose that G1 and G2 acts the same way on the algebra of functions. But in order to check that, if you want to, you want to prove that G1 is equal to G2, but in order to check that they're equal, you can act on any element of G, yeah? So, yes. And then you can apply functions to this. Yeah? For any f. And you know that they act the same way on functions. Yeah? Но вот это действие на функциях.
Мы в другую сторону хотим.
Сейчас.
Нет, ну как бы
Мне,
это...
по-моему, должно быть нужно то, что на алгебраическом многообразии функции, где
на афинном алгебраическом многообразии функции разделяют точки. Поэтому.
Вообще нигде не используем сейчас.
Почему? Мы используем, что чтобы проверить, что они равны, вам нужно проверить, что применение к ним функций для всех функций равны. Но это так, по вот этому.
Там, наверное, можно просто вместо длинного x написать e просто.
Ну, можно e написать, да.
Да.
Да. Не, ну x тут даже вы можете показать, что они действуют одинаково. Да, да. Поточечно одинаково действуют. Ну, то как бы тут избыточная информация, тут информация о всем действии, ну, как бы вот на всей группе. Yeah, so what I wanted to say that now, now we have to prove the case of, so consider the case of G is equal to GLV and relate it with Jordan decomposition. So relate with Jordan decomposition. So here the situation with the Lie algebra is parallel. Yeah? So your Lie algebra act by derivations on. This is just derivations of the algebra. We again say that the element is nilpotent if this holds for any finite dimensional vector space, and the element is semi-simple if this holds for any finite dimensional vector space. So here, so the situation with G is a little bit more tricky with the Lie algebra. So we want to relate it with Jordan decomposition. Then if you have element of A in GLV, which is semi-simple, or, well, respectively unipotent, then if you consider how it acts, rho of A acts on K of G, well, rho of G acts on K of G as semi-simple well, respectively unipotent operator.
How can you mention regular functions on GLV?
Yeah, so just a second, we shall discuss it. So just the difficulty of the proof is just what you have mentioned. You have to understand how we can just define the functions. Yeah? So in order to do it, so let us recall what are the matrices. Yeah, so what is the set of matrices on V? Yeah, so just what is n by n set of matrices. So this is endomorphisms of V. And in the same time, я приоткрою вам, нормально? А то что-то жарко стало. Yeah, so you have this endomorphisms of V, and notice that GLV acts on, here these endomorphisms of V are just the tensor product of the dual space and the space V. Yeah? So here you are thinking of the action on this set of matrices as the action here. Yeah? So action on the tensor product. Yeah, so in the same time, so you have to pick, how we define, so here raise, how we define the algebra of functions on G using the determinant. Yes, so we have, yeah, so recall that if you have the affine variety and the f is a function, you can identify the set of x without the zero set of this function as follows, as simply as I mean the algebra of functions on this affine variety. We are saying that you are taking kfx modulo the kfx with additional variable modulo ft minus 1, yeah? Or equivalently it is just localization of kfx in f, meaning that these functions here are just written elements of the form phi where f taken to the power k. Yeah? So where phi belongs to kfx. Yeah? Okay? So this is passing to the complement of the open subset. And when you're thinking about GLV, it is just matrices, n by n matrices, without the zero set of determinant. So this means that you have to take k of this vector space, the functions on this vector space which in the endomorphisms of V, and which is k of V tensor V dual, and localize it in the determinant. Yeah, so take this function and localize it. Yeah, so if you have the vector space, yeah, so what happens if you consider the polynomial algebra? Then this is isomorphic to just saying that you are taking symmetric power of the dual to the vector space. Yeah, so this is written as follows. So this is symmetric power of V tensor V dual. And then you take dual and then you localize. So you are adding, you are allowed to take denominators. But then you have to understand, so let us notice what happens. This one? Ну, это же просто как бы полиномы, то есть они же симметричные. Ну, то есть вы берете базис из моновов и как бы разрешаете. Ну, вы берете набор координат и разрешаете писать все мономы от этих переменных. И все симметрические мономы. Поэтому это как бы...
Почему только симметрические? Мы же на длинном пространстве.
Нет, ну функция.
Функции x, y и y, x это одинаковые.
Да.
Ты их там на векторе, не знаю, 1,2 посчитаешь, одно и то же получится.
Вот. Да, еще тут вопрос был какой-то.
Между третьей и четвертой строчкой стоит знак равно.
Вот тут?
Нет,
Вот тут. А, ну в смысле, что, ну как бы... Да, и вот тут надо локализовать. Да. Yeah, so then you have this kind of thing, and you want to understand what is the type of operator. Yeah? So if you take, so in order to see, to prove our theorem, we have to notice that if A is semi-simple, then the action on this set is semi-simple, and if A is unipotent, then the action, so if A so is semi-simple on V, then it is semi-simple on, well, let me put it, K of GLV, and the same, so unipotent. Just a second. Yeah, so so notice that this kind of identification between endomorphism and V tensor V was canonical. So it commutes with all the actions. So we, if you just yeah, so A acts on V via the usual formula, on the linear function, yeah, so on V dual via the formula that A applied to linear function that acts on V is just L of A inverse, yeah, because it is the element of the group. You want to have an action. And if you want to have an action on the tensor product, yeah, so you see that it is sufficient, yeah, so on any tensor product actually, yeah. So if you want to define the action on the tensor product, then you define it on the, so any element here is the linear combination of lambda I Vi Wi, and the A acts on the monomial wise, yeah, so just on the tensor product, just like this, yeah. And from the viewpoint of operator, if you think of when you take this identification, so when you take, so how does the identification of V tensor, V dual tensor V and the endomorphism look like? Yeah. Yeah, so you may write explicit, закрыть. Yeah, so you may write it explicit, I mean you may write it via functorial property, but here it is easier to write down in this direction. It's not easier, but I mean for me it's more convenient now to write down it as follows. So you have to just say what does it mean, the value of this operator on W, on the element W, where W belongs to V. So V is an element of V, and this is an element of the linear function. It is just applying Li to W and multiplying by Vi, taking the sum. And you see that if you are acting this way, yeah, so you just have to take this definition, and combine it. You see that that you are acting on the argument by A inverse of W and by A on Vi, which corresponds to action on matrices. So if B is a matrix, then this is A, B, A inverse. Yeah? So this all is consistent. Не, я не... Ну, как бы меня спросили, как на эндоморфизмах действует, ну что, я увидел, что вот на эндоморфизмах я должен определять, ну, у меня вот есть векторное пространство, на нем как-то надо определять действие на V со звездочкой. Ну, если у вас есть действие на... So if you have action on V, you have to define action on V dual, you have to define action on tensor product. If you have matrices, so endomorphisms of V, there is a natural action by changing the coordinates, which is conjugation by the matrix. And I have noticed that the actions I have defined here are consistent with the action I have defined here by conjugation. Понятно? Ну, просто как бы это проверка корректности того, что мы... Я не хочу не с этим работать, а вот с этим. Ну, как бы, поэтому это проверка корректности, что ну, действия здесь и здесь согласованы. Да? Да. Ну, априори там можно было бы как-то глупо действовать, например, на одном из аргументов. Ну да, просто проблема в том, что the problem is that here on abstractly on V tensor V there are many actions. So you can act only on this factor with neglecting this one. You can act only on this factor neglecting this one. So I'm saying that I have chosen action here via these properties, which is really the action what I wish to have here. So this is just observation. Yes, so this is some kind of check. And now I have to notice, now I have to do the following. Now I have to understand what is saying that you have semi-simple operator and what is unipotent operator and how it is related with all of these operations. Yeah, so if A is semi-simple, then on V you have the diagonal basis. Yes, so there exists basis. A V lambda is lambda V I. So this basis. If it is unipotent, then you can speak about eigenvalues 1 and or just u minus a minus 1 in the power n is equal to 0. Yeah? So what happens with dual space? Yeah, so on dual space, there is dual basis. Yes, so just basis on dual basis to Vi. Yes, so these are the set of functions Ci Vj that gives you delta Kronecker symbol. Yeah, so this gives you on dual basis you have it gives you diagonal basis clearly with so you just pair these equations with Xi I and you get that Xi I are dual basis with eigenvalue 1 minus 1 minus I. So this so this is precisely the basis. So if you have the tensor product and just something diagonalized here, so Vi is eigenbasis. And here you have another eigenbasis. Then clearly, if you act like this, yes, so you're acting on Vi tensor Vj. Yeah. So this gives you lambda I mu j Vi W j. So this gives you eigenbasis for the tensor product. Yeah? So then basis for tensor product. So similarly, if you take the symmetric power, so if you consider symmetric power of some vector space where this vector space is diagonalizable, so Vi is eigenspace and space. So the monomials, of course, Vi1, V1 alpha 1, etc., Vk alpha k. So the corresponding monomials form eigenbases with eigenvector lambda 1 alpha 1, etc., lambda k alpha k. Yeah? So so we have checked that all the operations that are obtained here. So if you have eigenbases, you can construct the eigenbases for the action on the tensor product, on the symmetric power, on the dual, and these are precisely operations that we used here to pass from this algebra here. Да? Понятно?
Откуда там минус сделать?
Ну, потому что А в минус первое, оно действует как, извините. Потому что А в минус первый действует. Да. Что А на L, В, по нашим правилам, это L от А в минус первый, В. Вот по этим глупым причинам. Окей? То есть вот как бы мы... so if you speak about unipotent elements, so if your operator, so if you have operator that is nilpotent, so clearly if it is nilpotent of bounded degree on V, so for any V, so this means that again, so if you apply L of a to the power n, V, then it is equal to 0 for any V. Yeah? So unipotence is also preserved. Yeah? So when you define the action, the nilpotence is preserved. So nilpotence is preserved. Yeah, so of course here you have to notice, in order to be consistent, you have to notice that if there is a small exercise that if you have A minus, so if U is unipotent, then U inverse is unipotent. Yeah, so I mean, it's not so, just completely evident from our definition. Yeah, so then U inverse is also unipotent.
We want to find basis not in symmetric power of V.
Нет, здесь, как бы, для вот этого мы хотим, да?
Нет, мы не там хотим найти базис.
Ну
Мы
как?
хотим найти в любом конечном векторном пространстве. Инвариант.
Для этого, как бы, для этого достаточно сделать следующее, как бы, yeah, so of course you are asking, yeah, so there is another part, I mean, just, yeah, so if, yeah, so the thing is that if you have, Yeah, so let me write it down. So this is additional remark. Не, ну пока так, то есть пока я там хочу, как бы, а еще есть. So there is additional remark to make the final goal. So here you have, so suppose you have the operator. So suppose you have V that you decompose into the direct sum of Vi. Yeah? So such that your operator maps Vi into Vi. Yeah? So this is invariant decomposition in the direct sum. Yeah? So suppose you take W, which is A invariant. Here, so just here let me put it. Yeah, so let me put it for eigenspaces. Yeah, so just so let us decompose V into the direct sum of V lambdas, where A acts on this space by mapping V into lambda V. Yeah? So suppose you have a W which is an invariant subspace of V. Then I claim that if you take so you have decomposition into V in the direct sum of V lambda intersection with V. Yeah. And this is just so this is done separately. Yeah. I mean this is separate. I mean. Just this is the following observation, so let us put it as an exercise. So this is precisely describing all invariant subspace. So if you have V which is decomposed into eigenspaces where on each V it acts by the scalar, then V lambda is just decomposed like. Huh? Oh. Okay.
What's defined?
Just any A invariant subspace of V. Yeah.
And it is enough to prove this exercise?
Yeah, it's enough to prove exercise for finding any. So to proving that.
For finite dimensional V.
Yes, because this. Yeah, so this for finite dimensional V, because this is decomposed into the direct sum of symmetric powers. Yeah. I mean, if you have finite dimensional subspace, it is contained in the finite sum of these subspaces. Yeah. So you have to take only finite number of these subspaces, and you are done. Yeah. So you reduce it to finite dimensional case.
А локализацию вы пока еще не трогали?
Пока еще не трогали. But localization here is yeah. So localization is just is fairly easy here. Because if you think of, so you may take the just any subset. So let us pass to localization. So here you. So you want to pass to localization, but localization comes via taking 1 over determinant. And if you pick up eigenspace, so eigenbasis here, So so this is the invariant subspace. Yeah? So if you take this localization, determinant is semi-invariant. Yeah? So if you act by GLM, then determinant, the determinant, yeah, so if, so if you act by GLN on determinant, it will be multiplied by the determinant on the corresponding operator. So it is semi-invariant. Yeah? So if you just look at the value, yeah, so the determinant was taken on some b. Sorry, here it is just invariant. Yeah, so on the determinant you act like this. Yeah, so you take b and act by the matrix A like this. So the determinant is just fixed. Yeah? So if you have this eigenbasis, so they will play a role. So if you have, if you take f, so this will be an eigenbasis of so if you divide by determinant, so this will be an eigenbasis of the subspace generated by determinant in the power L. Yeah? And everything is filtrated by this kind of subspaces. So you are done. Yeah? So everything can be put in just in the union of such subspaces.
Why did you use the determinant is invariant?
Because these are eigenvectors, then these are eigenvectors. If these are eigenvectors, then these are, when you divide by the determinant, they're still eigenvectors. Yeah, because in order to check that they are eigenvectors, yeah, so you have to take them. Yeah, so you have to take this f. You have to write down gx. And as the function on determinant, you also have to write down the action on the determinant by your so determinant is the function on your matrices. So you are just writing down the action on G on the matrices on here you are writing down the action on the determinant of these functions. Yeah? So I have written here as a left shift, but it is erroneous. Yeah? So I have to write action, which is the action, that comes from our action on endomorphisms. So just. So the second part is to understand everything for unipotent operator. So if this is unipotent, so U is unipotent, then U inverse is unipotent. And when you act as on the linear function, then if you have you have to check that if A acts is nilpotent on V, then A V and W, so then A is nilpotent on V and the tensor product, and symmetric power. Yeah, so on V dual it is clear. Yeah, so you have to check that a to the power n of L on V is just L of A of V to the power n, and this is equal to 0, since it is here 0 here for any V. No, it's this doesn't make sense. Yeah, so you see that your action should be taken via U inverse. Yeah, so A here is just is not 1 minus U. Yeah, so A here is I wanted to say that A is yeah, so A here is U minus U inverse minus 1. Yeah. So in order to check that the operator is unipotent, you have to check that you have to check that a U inverse is unipotent. Yeah, so this is sufficient to check that the action of U inverse minus 1 is nilpotent. Yeah, so by definition, and you are applying this operator, and you are checking that this is indeed unipotent. Yeah? So this is nilpotent, just because of this thing vanishes. Then if you think of the tensor product of V and V dual, yeah, so if if A is nilpotent on V and W, then A of in the power V is just yes, you are acting diagonally, so it is clear that it is nilpotent. And the same thing for symmetric power as well. Yes, so it's clear that this thing is nilpotent. And also, you have to notice that when you pass from the basis f lambda 1, oh, sorry. So when you want to pass from in the localization, so localization part, so you want to pass from k of v to localization. So yeah, over determinant. So notice that you can pick up vector here, and here you have to consider vector f divided by determinant of L. So if you want to check nilpotence here, so you are acting by A to the power n on this operator, but this is nothing as A to the power n acts on F, A divided by A acts on determinant. And if you are acting by unipotent, I mean so if you are acting by unipotent operator here, you notice that you are acting on this unipotent operator, but unipotent operator has determinant 1. Yeah, so this is just UF divided by corresponding determinant. And so this tells you that if you want to check the nilpotence of the operator, you just subtract 1, and you see that it is if U was nilpotent of F, it is if and only if that U minus 1 is nilpotent of F divided by the element which is invariant under the action of U. Yeah, so just yeah, so you have to check that u minus 1. So you have to be able to write down u minus 1f divided by determinant, but this is nothing but u minus 1 f divided by determinant, because determinant is invariant with respect to u. And if you want to take power here, so this is the same, so this is equal to 0. And this proves the nilpotence. Okay? So this shows you that so this shows that this operation is well defined, and for GLN, and next time we shall briefly discuss why it is true for how it defines the Jordan decomposition for arbitrary group. Okay.
So we don't prove that it exists.
Нет, ну вот в следующий раз мы уже можем показать, что оно существует.
But we prove that it exists for subgroups.
Да. Но оно, ну, в смысле для GLN, вот оно как бы вот такое. Но это уже просто 2 минуты, я просто не хочу уже вас держать, передерживать.
Да, там уже следующая пара сейчас.
Угу.